and then we can do private ones after. Yeah, so you can say, ask louder so others can hear as well.
For the C-space transfer,
Yes.
expand.
Yes, you're right. This doesn't look right. Correct. Yeah, it should look like this. Yes. Yes, it should look like this. Yeah, this is wrong. Yeah, this is, I think, from a book. I didn't draw this. But yes, you're right. Yeah, it should look like the blue region. Yeah, it's slightly wrong. Correct. Question? Yeah. Yeah.
So actually, I asked this question of the other. It's about we know that we need to figure out the state by ourselves. But in B, the requirement that we only use one control policy, meaning we can in a given pair of time and state, we can't map cells to different control inputs, even if they are different environments.
Well, depends on your state, right? If your state is defined not only by a cell, but other information, you can.
Yeah,
Yes.
so the TS, yeah, so I was thinking, if we really, there has to be some way to incorporate the information of the position of the key and door and go into the system, right?
Exactly.
But I think just putting it as a element in the state vector is kind of silly, okay?
Right, yeah, because it's going to be much larger than you need it to be. That's right.
The same across all maps. So if I use it as an external variable, then it's essentially the same as A, right? It's nothing different.
Well, you should not, yeah, if you use it as an external variable, yes, but you shouldn't use it as an external variable. You should make it part of your state. But let's think how. Let me give an example, I guess. Second. Right, so the question is in part B of the project, how do I represent states associated with a key position, door position, and so on. So let's start before that. Let's say I had a completely empty map. There's no obstacles, no doors, no keys. I just need to get to the goal. What would be my state then? It's a question for everyone. Yeah.
I solved this problem by constructing a state space of size width times height times 4. Because in one cell there are 4 directions.
Exactly. So my state will be position, which is two-dimensional. Where are we in the x-axis? Where are we in the y-axis? And orientation, which can have one of 4 values, right? So I can think of my state in an empty map like this. So x is some number from 1 to how many cells are there? 16 or 8? I forgot. Y is some value from 1 to 16, and theta is some value from 1 to 4. So now my current state is x, y, theta. And how many possible states are there? I think you said it. Yeah.
The width times height times the number of.
Right, 16 times 16 times 4. That's all possible states right now, okay? Then what if we have more things? So now let's say we have a door, but we know where it is. So then what should I add to my state? Is it open or closed, right? So how should we denote that? So I have a door.
0 or 1.
It's either 0 or 1. So now what is my new state? It's x, y, theta, d. And how many states are there now? Possible states. Times 2. Yeah. Okay, what if I have a second door? And I also know where it is?
Times which.
Then I'll have d1 and d2, right?
What about if you had a key?
Yeah, what if you have a key, and for key we care about position, right? What should we do then?
I don't think it's necessary to put the status of a door into the state space. It's just adding the dimension of the state space. Because once you know the door's position, you don't have to make it for all other cells that are for door.
But that's using external variables, right?
Sorry, let me make sure I understand the question. Say again, once you know the door's position?
It's a closed door. You can
Yeah.
just treat it as a wall.
Okay, well, still you want to know if the door is open or closed, right? If the door is open,
But for other cells that are not doors, you don't care about whether it's open or closed, so you don't have to. I think if you add one dimension of whether it's open or closed, it's adding the computation complexity.
Yes, but you're not adding, so D here is not, you're not adding this for every position.
But this.
So we're multiplying by 2 because you can be in position 3, 3 and the door is open, or you can be in position 3, 3 and the door is closed, and those are 2 different states. Does that make sense? It doesn't mean that there's a door at 3, 3, there's a single door, but those 2 states, I'm here at 3, 3, the door is open, and I'm here at 3, 3 and the door is closed, are 2 different states. Yeah, that's why we distinguish them. Does that make sense?
I guess a follow-up to that question would, it would be like, you would want to know the state of, you would want to include like your door as a state, so then like when you're actually doing dynamic programming, and you like start at the goal state and compute backwards, then like, you start off addressing all possible states that the robot could be, and it could have reached the goal with the door closed or the door open.
Exactly.
If there were paths leading to the goal with the door closed, right?
Exactly, exactly. Yes. So yes, you do want, especially in part B, you want to have everything in your, everything that matters in your state. That's right. Yeah. So I guess that's my hint. Let's maybe answer Dallas's question about what if there's a key as well, and then we can be well. Let's simplify this even a little further. So we could denote the position as P that goes from 1 to 16 squared. Okay, just to simplify things a little. So I made P a linear index along the map. And then what about the key? So how would I denote the key? Yeah, position of the key, how should I represent that?
Don't you want to keep, like, whether you're holding it or not, and not the position?
Okay, maybe you want to keep that as well. Okay, so let's say we can have a variable key hold, something like that, which will be 0 or 1, right? And we can also have a variable which tells us where the key is. So what would that be? So let's say key position, and in part B, how many possible key positions are there? 3. So you could live, I don't know what they are, but for example, they give me 17, 77, 18, and 3. So these are your possible key positions. Yeah, because I was assuming it can be 16 by 16. Yeah, it should be 8 by 8. Yeah, so your space is smaller. Yeah. I think maybe let's go. You had a question, right?
Oh yeah. So when the door is closed, the robot cannot be at the position where the door is at, right?
Correct.
So then the state space of the robot could change. There shouldn't be like 16 position. There should be like 16.
Yeah, technically yes, but I think it's too
Or
difficult to do this
Still
book.
treat it as a state, but only the cost. to
Exactly, yeah, you could
infinity.
say it's an allowable state, but the cost of getting there is infinity or something like that.
oh,
So you can allow, yes, there exists a state where the robot is on top of the door, but getting there costs infinity. I would say that's easier to
So
deal with
yeah.
than,
okay.
because then you have to, yeah, you're right, technically it will be 8 by 8 by 4 by 2 minus 1. Because there's one state that, but then it's really hard to enumerate them.
So
you're
in
making
this way we can just formulate a problem in this way, and which is easy to solve.
It'll be easier to keep track of the states this way,
And
yeah.
And also why it's like 77, 18, and 3.
I chose random values. You can look at, in part B, there's some particular places where the key is. Well, those would be
Oh,
those.
okay. Oh.
Yeah, I don't know what they are, but yes, I picked some. Yeah, shouldn't we go first?
Question about the work on the example that you raised that if possible you have to include over the every frame, like for given a map and an action sequence, for every frame of an action you have to include a
Yeah,
figure.
yeah.
I think that's too
Maybe too much, yeah, not for every frame, but you can pick a few. So in terms of visualizing results, right? So for the report, right, to show your results, there are 2 ways, and you want to have a little bit of both, quantitative and qualitative. So qualitative means show me a few pictures of this environment. So if I'm in environment 1, I can show something like time 0, time 5, time 10 and time 20. I don't know, pick the values for something that looks reasonable, but I can show like 4 small pictures side by side in my report, which shows kind of what happens over time. But yeah, the counter here doesn't have to be 0, 1, 2, 3, 4. It could be 0, 5, 7, 8. Yeah, so you can pick
So
some.
there are 43 invariants in total.
Yeah, I don't think for the random ones you need to show it for all of them. I guess we need to revisit.
So
Yeah,
can I
need to-
just show the action sequence for each map?
Yes, you can show the action. So to show the action sequence, yes, right. So to visualize, you can just do a subset, but then you can, for every map, then you can say 1, 2, 3, right? So you can make a big table. You can make a big table here, which, let's say you have map A1 up to A7, and then you have B1 up to B36, and then you can have sequence. Well, it depends on the start as well, right? Did we give you a particular start for the
Yeah.
maps? Yeah. So if you fix the start, you can have the sequence here, and so on. Yeah. So you can build a table like this. And I was
we
saying.
don't have to show all the states for random maps for 36.
Is in show you mean have figures?
Like every state.
You can show the action sequences for every map like this in a
I think
table.
in this way it's much.
Yeah, this is good.
It's like
And then I would select a subset. So let's say all the maps in part A and let's say 3 or 4 in part
Isn't
B.
it?
Then you can show, let's say 4 time steps from each. So then if you, let's say 7 from part A, 3 from part B, that will be 10. And you pick 4 time steps for each. We have you have like a figure that's 10 by 4 or something.
He just got it.
Or, I mean, of course, you can split it into
How
several,
much is it?
into several pages.
I don't know, it's an
Does this go? I think maybe he was for you.
Yeah, so we'll go back to the previous slide.
Previous slide, yeah.
Cost like- That looks like 700, 800.
It's free for me.
Previous slide here.
Oh, no, I mean your handwriting for.
Oh, no, I didn't say that.
So, okay, I can just. So you said that you are putting the key position as an element in the state vector, right?
Yes.
So I think, this is very inefficient. For every state, we put a position there. Why don't we just use the external variable, and that would just be one variable, just an integer, and instead of in every state, like an integer times the number of cells.
Oh, because my key position have only 3 possible values, but if you keep an integer per state, you have 8 squared
Yes,
values.
but in order to not use external variables, you have to put it in the state. Otherwise, where do you put it?
I'm not sure if I understand the question. So I would have those 3 variables be part of my, the key position will be part of my state, yeah.
Yeah, but like, if every position agreed, there will be a state value or.
No. So there's no state in every, so I think it's similar question that Julie asked earlier. One second.
It's more, right? I think it's a number of cells in the grid times 4, right? That's the number of states in the MDP.
I think there's only 3. Because like we're given the possible position of the keys.
Yeah, but like, how do you access that value?
Yeah, I understand your question. So let's say so it's good to think about particular cases that are simple. Okay, so let's say we have this map. There are 4 positions only, so it's a 2 by 2 map, and we have a key in one of the, we could have key here or here, right? Okay, so key positions are 2 possibilities, and the positions for the robot are 4, and let's ignore the orientation for now. So how would I represent the state space here, right? I will have one variable P, which will have values 1, 2, 3, or 4, right? Let's label these like this. And then we'll need the key position, let's go K. And the way I was suggesting is that this is either 1 or 2. So the total number of states here is how many?
8.
That's right,
Eight.
4 times 2, right? And the other option is what you were suggesting, which might be good as well. Let me just make sure I understand. So what was your suggestion? You want to introduce a variable K to say what? It's binary for every position, right? Or
It's
yeah,
not
so
for
your
every-
case-
It's not for every position, but for every state in the MDP.
right, which is 1, 2, 3, or 4 right now, I guess.
if you are not considering orientation.
I'm not considering orientation right now, yeah.
Yeah.
Right, so let's say you have 0 or 1, but it corresponds to every state.
Yes.
Yeah, I don't know what that means actually, because your K is not actually this. You have, I think what you're saying is something like this, right? So K here will tell me there is, no, actually even more than
It's
this.
a fixed value, right?
Hmm?
I mean, it's just the fixed value, it just puts the coordinate of the actual key as a element in the state vector, and it never changes, it doesn't change along with any, with position, no matter
Right,
what position.
so that would be something like this, right? K is 1, 2, 3, or 4. This is the position of the key. So then my state is P and K. And the possible states are 16. So you have more. So how do you represent, maybe I don't understand your
Sorry.
representation. So how do you represent your key position?
It's, the key position is fixed, right? You know, map is fixed, it's put there, and if we pick it out.
No, but in part B, the key can vary, right? Position can be,
Okay, so we don't know where the key is before, when we run algorithm.
correct. In part B, we don't. Yeah, correct. In part A, we don't need to represent the key. We know it. Yes, we don't need to, it does not need to be part of the state in part A. Exactly right. In part B, that's no longer true. The key can vary. Yes.
So we don't really know the map, we don't really.
Well, we don't know the map. Yes, we know the map is one of 36 possibilities, but we don't know which of those.
So we can't use a even V dot, like those, you know, the getter for the key position.
Well, we can use that. Yeah, you can look up where the key is, but you are not allowed to replan or redo your algorithm. So when you're formulating your control policy, it has to be without knowing where the key is. Does that make sense? Because you're applying one policy which will work on all maps.
Okay, thank you, yeah, just in case.
Yes.
But it will be out of those 3 locations, right?
Correct, yeah. We know that in the random maps in part B, the key can be only in one of 3 places, right? So when I was giving examples, I was showing how to encode that.
So is
Yeah,
it something,
No, go ahead, yeah.
so is it something like we have to plan something like a sub goal and final goal, something like that?
No, so project 1, by now we've discussed a few more algorithms, but project 1, at the time it was assigned, and the idea of it is to test you on the dynamic programming algorithm. So on the algorithm side, there's nothing to think. You should use dynamic programming.
Is it like you have to tell the shortest path or just the least?
No, there's no shortest path, dynamic programming. So there's only one algorithm, dynamic programming. The main question is how to represent things. In dynamic programming, there's no notion of goal, right? There's no such thing. Right. Let's see. Maybe
Once we have generated the random environment, we know the position of the key. We have the 3 locations the key can be.
exactly.
We can check the value of each cell, and if the key is there.
But it might or might not be there because you don't know which of the 36 maps you're going to get.
It has to be out of those 3, and we can check those 3 cells, so we know where the key is. And we can fix that.
No, so you're coming up with your policy before you know which environment you're going to get.
Also, the policy should be made before the environment is also.
Correct. In part B, you need to plan it. You need to compute or construct a single policy which works for all maps. But you're not allowed to look at the map and then come up with a new plan. Does that make sense? Sorry, it's your turn. Yeah.
I was quite confused about could you give some hints on the motion model?
On the motion model, I think the motion model, I would keep it pretty simple and introduce what's allowed and not by the cost. So motion model is just
Multiple if then if else.
yeah, the motion model is just let's think about it. So okay, let's denote our position. Yeah, we need position and orientation, right? We said our state is something like this.
Theta is what the
Hmm?
theta means like the.
Yeah, we can be oriented
We
forwards.
are
right?
allowed only one way.
We can face up, down. Yeah. 4 orientations and positions are probably even less than this, right? I think all maps have a boundary on the outside, so you only need to look inside. So really, this is more like 4 squared. Okay, we're going smaller and smaller. Let's see, what was the question? Oh yeah, motion model. So what is the action space or the control space? We have 5 controls, yeah, well, I forgot what they were.
Forward, turn right, turn left, take key and unlock.
Okay, we have these 5. So what is the motion model? So what do we call a motion model? It's a function which tells me what?
Which state, like from what
Next.
state, from move to what state, given a control.
Exactly, right. So I would say define motion model. And the inputs will be x and u. And then what would I do inside, right? Yes, you can have yeah, you can think about how to represent the u's here, but you can have if and else statements here, sure. If u equals move forward, then I would say something like
xt plus 1 equal to xt
pt plus 1 is pt plus 1, 0. Okay, I'm abusing stuff here a little, I guess.
We have
that-
xy coordinates, so we can change the coordinates plus 1 minus 1.
Say it again.
Can change the coordinates, xy coordinates, plus 1.
Yeah, change to xy coordinates and then
Move
add
forward,
1.
say y plus 1.
Yeah, exactly, right. So that's roughly how I would implement the motion model. Yeah, I would look at the different options for the control and how the position changes, how the orientation changes.
I was thinking of one more thing, that we have 3 different positions for the key that can be done. So
Okay.
before starting, should we just put all those 3 places as a wall? Consider them as a wall and then look through all the places and then.
No, we don't have to consider the key locations as walls.
Because-
But our state X here, right, in part B, we'll have to include more stuff. So we'll have some.
Can the robot and the key position overlap?
No.
No, right?
It cannot, no.
Yeah, so we should consider it a wall, right?
Yeah, if you're not using
If
door.
we don't
and-
have the key basically.
Yeah, exactly. If you choose to not use the door and key, you have to consider that. No, but you can pick it up as well. You can pick it up, this takes 1 action, right? You can just go through it.
Yeah, but I guess to answer your question, in defining the motion model, you need to have a case where you say, if I have move forward and there's a key in front of me,
Yeah, we can define a if case, if like next, you are facing the key, pick it up, then move forward. something
yeah,
like that.
but I think, again, I would keep the motion model simple, meaning all moves are allowed, but then you can make the cost, the corresponding cost to be infinity, or vice versa. I would say keeping the motion model simple and then putting infinite cost is simpler to me, but either is equivalent.
Yeah,
Let's go
so
with your
the
question.
goal position is also random, right?
In part B, yes.
Yes, but so based on, I think like what you said for key, I think we will never know where the key, we cannot know where the key is before the agent actually encounters it, right?
No, we would actually, when a map is realized, so when you're executing your policy at the very first time step, you can look up where the key is and you would know right away.
So then I will store a external, then why do I not store an external variable at the beginning?
Because at the time you're running your algorithm, you don't know which of the 3 positions it will be. When you're building your policy, at the time you're executing your policy, you do know. Does that make
Okay.
sense? So it's kind of like playing a chess game tomorrow. You're coming up with your strategy today, so you don't know what your opponent is going to do. So you're predicting all combinations, and you're coming up with your plan. And then tomorrow you're starting a game, and you can see what your opponent is doing, but you're not changing your strategy. Does that make sense? So when you're planning your strategy, you're predicting all possibilities. When you're actually playing, you look at which is the one of the possibilities that's realized and play according to that, but you don't change your strategy.
Yeah, thank you. I think as long as we are using the same dynamic algorithm, we will not change our.
Correct, exactly.
It's pretty basic. As long as we are using that algorithm, we will not change it.
Right, yeah, so the idea is to run dynamic programming based on 36 maps without knowing which is the true one, save the policy, and then execute this saved policy on whatever map you get. But you're not changing the policy.
But with different positions.
Correct, exactly. When you initialize your map, you're gonna know where you are, where the key is, where the door is, whether it's open or closed, where the goal is, and so on. So your initial state is different, that's right, but the policy is the same.
That's pretty much the same with A, right? It's not too much.
Correct, yeah, the solution in the end is quite similar, but yes, your state space is larger.
Yeah.
So
Go for it.
my question relates to more so like the part of the algorithm of dynamic programming that deals with minimizing your costs.
Yeah,
And to me, like, let's just say you start at some given state and then you compute all possible actions that you could take, but then you wouldn't automatically be able to perform some sort of minimization
I
routine.
think in our case, we only have 5 actions, right?
Yeah.
So you would just look at the 5 possibilities and see which one is min over the 5, and that's it.
But like if they have all equal costs.
Oh, you tie breaking, you can do arbitrary.
Oh, okay. But like when it comes to like if you have, it's just a tie break. Okay.
Yes, that's just tie breaking, yeah. If we had continuous actions and so on, it's more complicated, but with only 5 actions, you just compare their values literally and pick the one with the smallest.
Oh,
And if there's several equal values, you can pick randomly.
But then, so now that you've said that, then like with dynamic programming specifically, like if we were to take every single like action that we could take as having a cost of 1, then basically our path, our policy from start to goal would be basically the amount of actions that you've taken.
Yes, correct.
So then with what you've said about tie breaking, then that would really imply that the solution that you get isn't actually like minimizing the amount of actions that you're taking to get from start to goal if you're just doing like arbitrary tie breaking, right?
No, the arbitrary tie breaking means that these 2 actions have the exact same cost. So yes, at the very first time step, all 4 or 5 actions will have the exact same cost, but when you start computing over a horizon, that will no longer be.
Okay, yeah. Like, I mean, like my thought is like once you've computed a bunch of different actions and then you land up in like those different computations end up in the same state, then you would be able to like accurately determine which of those 2 paths has a lower cost.
Exactly,
associated.
exactly. Yes,
Okay.
and that your value function will be storing exactly this. That's right.
Okay, but like that's only possible like if like from starting from like one distinct location to another, and it doesn't really take into account like well it takes into account like what specific turns you've made, but you can't immediately like just for making a turn you can't immediately just say like, oh, this is more optimal, like this path is more optimal than
Correct, exactly, yeah. Just by taking a turn, you won't be able to. That's why, remember in dynamic programming, we start backwards in time.
Okay.
So when you have 1 action left, and your goal is to the right,
yeah.
one of those actions is a lot better than the other ones, right?
Right, I mean like turning right versus going into the goal versus like starting on top but going to the goal straight, that's like 1 action versus 2, so that's more optimal, right?
Yeah, exactly. So when we're going backwards, it'll be pretty straightforward to. Yeah, I mean again, once you define your states, it's pretty much running the dynamic programming algorithm. You don't have to change the algorithm necessarily.
Gotcha, okay.
It's just, yeah, that does go for it.
Okay, so in terms of what Sugar was asking about the motion model, I was under the impression, because I studied the example.py for a couple days and was trying to decipher what it was showing us. And it almost looks like it's showing us how to, or I mean that we don't even have to write a motion model because it kind of wrote the step function for us. And then we just have to update like what a cost would be for each of those actions.
Yeah, for part A, that's true. In part B, you have to maybe modify this a bit because your state space will be larger.
Okay.
So you would also need, so if, for example, if the key, whether, let's say door is open or closed is part of your state, and you execute an unlock door action, you have to change that state in the motion model. Does that make sense? So if you have a door which is locked and you execute unlock door action, you have to change its state to now unlocked. And that will happen also in the motion model.
I mean, like that doesn't happen in, even if we know the dimensions, like don't we still have to make it a robust algorithm to like handle everything?
Say it again.
Like even like I get that in part A we're doing known maps, but shouldn't we still design our algorithm to like pretend like it doesn't know what the map is initially?
No, in part A you don't have to do that.
Okay. I just don't see how like we wouldn't design it that way. Like
So the part A and part B are very similar. The main difference between them is what goes into your state. So in part A, you only need to worry about agent, position, orientation, and whether a door is locked or unlocked.
Mhm.
In part B, you need to worry about more things. Where's the key? Where's the goal? There are multiple doors and stuff like that. So your state will be larger to include additional information about these new variables which can vary.
Okay. Why would we not need to know where the goal is in part A?
Oh,
I-
'cause we can look it up right away. In part A, we get one map. You can look up where the goal is, where the key is, and so on. There's no variations. The goal is where the map tells us. But
Okay.
in part B, we don't know the map, right? We have to predict what to do in all different scenarios.
Gotcha.
Yeah, one more suggestion, I guess, for people is, if you find even part A difficult, I would come up with an even simpler problem first. You can come up with your own problem, something like, you can define your map to be like this. Like I said, this is the goal and this is the start, and solve this scenario first. Like write a dynamic programming algorithm, motion model, and so on for this scenario, and make sure you understand and can solve this first. And you can even randomize it. Your goal can be either here or here. So now you have two possible random maps. Pre-compute your policy for those two cases. Make sure you understand the very simple scenario very well first, and then go back to part A and part B. So this, I think, should be a lot simpler to do. Yeah. Yes.
I have a bit problem understanding there's a thing called env, the env there in the code. What is that?
So this is the environment definition from the GIM package. So it tells you where the door is, the key is, and how it moves around. So it's the mini grid environment.
Okay.
Yeah, like it's your map.
Yeah, it's the
It's
map,
all map.
exactly right. Where are the walls? Where's the agent? Where's the
You
key?
can look at go to environment. And then go to
Questions?
nodes.
I think there's maybe a.
And then-
You guys have a class?
Yeah, we have a section.
That's
yeah,
what I'm saying.
Yeah.
Yeah,
or
so it gives you.
Okay, we can do one last question.
These are.
I'm happy to answer more, but maybe
And
we
this
can
is
move
where you
outside.
start, and then you have to, this is where you want to get
Why
to.
is it only 3? This is 3x3. This is not 5x3.
So it's 5x5 if you count, because these are walls.
Oh, these are
Yeah,
walls.
I know, I was tripping out yesterday. I'm like, what?
I don't. I still.
It's
What
it's
is
a
it?
it's a lot to like study before you can start. So like definitely study the structure of how it works. Because that took me a couple of days, and then I started doing
Reading the
the.
structure.
Yeah, because like you're given a lot of starter code.
Oh yes.
So you have to learn how the environment, like, cause if you notice an example.py, I thought it was like how to do an algorithm, but it's just showing you a bunch of stuff you can do to use later.
Oh, how do you like this is just
Yeah,
tell us
that's-
how to use like env.
So you remember we said like the first thing we have to do is build a state vector?
Yes.
Like we're gonna be using this stuff to do that, cause within a state you would want your position, your direction, whether you're holding a key. Like, let me see what chat says.
So we need to first come up with a definition about it.
Like these are the first steps that you want to do. Which is first one is what you were saying, like come up with a state vector to represent your state. So that's gonna hold like position, direction, key status, door status. And then here, this is where you define your like actions that you can take. So that's why I was asking, like, didn't we already do that here? Because like this uses steps.
Yeah, because I think the stack is
Thank you for
here.
coming.
Yeah, I have to answer more questions, but let's go outside because there's a class.
Nice meeting you.
And we'll just tune in, you know.
Oh, okay.